Hello and welcome to EENG 4392 Smart Grid Systems. In this course, we'll connect the fundamentals of power systems with modern smart grid technologies, operations, sensing, control, and cybersecurity. I'll also highlight why reliability and resilience matter using real blackout case studies. These materials are adopted with permission from Professor Lee, and I'll add context and examples throughout. Let's start with why power system operations must be secure and reliable. The power grid is the largest machine on Earth, and the baseline expectation is simple: keep the lights on. When the grid fails, the consequences are immediate: safety, transportation, health services, communications, and the economy. We'll anchor this motivation with two landmark events: the 1965 Northeast Blackout and the 2003 Northeast Blackout. First, a quick overview of what happened in 1965. In 65, a major disturbance caused a significant disruption across a huge region. It impacted areas including Ontario and 8 US states. Roughly 30 million people were without electricity for up to 13 hours. This gives the first concrete example of how interconnected grids can experience wide area failures. Beyond statics, the human impact is important. Let's look at what it looked like on the ground. These photos illustrate the real-world consequences: computers stranded, mass transit disrupted, and emergency service dealing with elevators and building safety. The key message is that reliability isn't just an engineering metric. It directly affects public safety and daily life. Now, let's compare this with the much larger 2003 blackout. The 2003 event was broader and more severe. About 55 million people were affected, with restoration ranging from hours to days and in some cases longer. Importantly, it triggered long-term regulatory and reliability changes: the Energy Policy Act of 2005 and the creation of mandatory reliability standards through NERC. To understand why it escalated, we'll look at the sequence of events. This is a classic cascading failure. This timeline shows how a cascade can start from operational and situational awareness failures. First, an incorrect telemetry causes the state estimator, which is a monitoring tool, to become ineffective, and it wasn't restarted. A major generating unit trips, and then multiple transmission lines trip due to tree contact and sagging. Alarms failing and poor coordination reduce the operator's ability to respond early. The takeaway: reliability depends on tools and processes and vegetation management and coordination, not just hardware. Once the system reaches a critical point, the cascade accelerates dramatically. Let's continue with the timeline. After key lines trip, power flows redistributed rapidly, causing overload voltage collapse and protective trips across several regions in Northeast. Grid separations occur and generation trips as a protective response, creating a supply-demand mismatch. If you note the timescale, the system can move from stress to failure in just 6 seconds. You can see 4:10:38 p.m. to 4:10:39. p.m. So in just 1 second, you can see that it's just cascading and getting worse. This leads naturally to the big picture structure of North American power systems, and I have actually found a very good video that shows the sequence of events for the 2005 blackout, which I'm going to play.
Of what appears to be a colossal and history-making blackout.
People trapped in elevators and buildings, they have activated the emergency command center.
You're staggering trying to take in as much information as you can.
Mayor Bloomberg's advice is to go straight home.
The subway system is down.
Ottawa is completely without power.
The lightning-quick domino series of failures.
You gotta go to the bathroom and you can't even go nowhere.
50 million people are thought to have lost power.
In 2003, a massive blackout struck major areas of the U.S. and Canada and was perceived as a wake-up call for the nation.
We've got a real crisis in our grid, and this is why, despite being a super, we have a grid that is comparable to a third world country, and that's not right.
But have 10 years of planning and preparation left us better off today?
I don't think you can ever say with 100% confidence we won't have a blackout.
Electricity is really far more important than anyone realizes. We take it for granted, we flick the switch and it goes on, but it has to be in balance or the lights go out.
There has been a massive power outage throughout much of the Northeast, both of the United States and of Canada. Millions and millions of people were caught by surprise when the electrical grid suddenly crashed. It shut 100 power plants from Ottawa down to Cleveland and as far east as New York.
The most immediate concern was for thousands believed to be stranded underground in the dark in the New York subway system or in elevators in skyscrapers.
The attacks of 9/11 were pretty fresh in everybody's mind, and the first thought on almost every New Yorker that I spoke to's mind was, is this terrorism?
The police are saying that the evacuation procedures are working, people are calm, and that they are getting out.
A normal August afternoon had turned to crisis. Around 50 million people across the U.S. and Canada were left without power.
All of Cleveland's water supply runs on electric pumps.
My water commissioner said the people in the Heights have water for 3 hours. I said, water? I thought the electric was out. He said, Mayor, how do you think the water gets from the lake to the people in the Heights?
You can get along in the dark, you can get along in the heat, but water becomes a health and safety issue very quickly.
While terrorism was soon ruled out, there was a frenzied search to unravel the mystery behind the source of the blackout.
We don't know yet what went wrong, but we will.
What we're hearing on the radio is that there was some sort of incident in Ontario, Canada.
There was a lot of finger pointing.
U.S. officials initially accused a mishap at a Canadian utility plant. The mayor of Toronto fired back. Tell me, have you ever seen the United States take blame for anything?
It took 29 hours for the power to be turned back on in most major cities, but the brief outage contributed to at least 11 deaths and cost an estimated $6 billion in economic losses.
We were fortunate that the grid stayed up as it did and it didn't continue cascading any further.
Engineers spent months unraveling the cause of the blackout and traced it not to New York or Canada, but to a downed power line in Ohio.
The theory was it was a tree in suburban Cleveland. And we were like, what?
The official report later found it was a series of human and operational failures that set the blackout in motion. A downed power line went unnoticed because the alarm system failed at the local power company, First Energy, and soon other lines were overloaded.
When the line overheated, it sagged. And as it sagged, it hit a tree that shouldn't have been in the right-of-way corridor.
Meanwhile, at the regional service operator, Midwest ISO, an employee had gone to lunch and forgot to turn back on the tool that monitored grid problems.
As the grid in Ohio got less and less stable, with too much voltage over too few lines, power plants began to turn off. And eventually it cascaded around the Lake Erie Loop and all the way to New York.
Investigators said today this nation's worst power blackout was most the First Energy Corporation of Akron, Ohio.
First Energy was busy trying to grow, trying to absorb, and the report found that they had let many basic things go. That included tree trimming under these power lines. Their computers hadn't been upgraded. It was more than that.
First Energy declined to speak with us, but has publicly said it implemented new safeguards. Many saw the blackout as emblematic of a wider problem, one brought about by a lack of government oversight for years in the electric industry.
The standards are voluntary and not enforceable.
It's like expecting your kids, when you walk out of the room and leave a pile of candy, not to help themselves, unless you've said, there will be consequences if you grab that pile of candy.
First Energy was never fined for its role in the blackout. In 2005, Brownell's agency, the Federal Energy Regulatory Commission, was finally given the power to impose hefty fines and has levied tens of millions of dollars in penalties since 2010. But fundamental issues remain.
It still doesn't quite make sense to me that the grid was that vulnerable.
It's a big old system. When it started, you had a little local system. You had an electric power provider, a plant, a spider web of wires around the plant to serve customers near the plant. Then you put together a national system where you connect all those spider webs. It's grown up over a long period of time, and there just isn't one center or one organization or one entity that's in control of the whole system.
There have been improvements since the blackout, including those that allow power companies to better monitor. The goal is to use that information to redirect power across the nation's grid in real time to stop blackouts before they start.
At some point, there may be a breakthrough where it becomes very efficient and effective to store energy, in that you'll be able to shift energy uses to different parts of the day as one grid, as one system. And I think that will dramatically change how this industry is operating.
We have perhaps $1 trillion that needs to be invested in the electric grid to bring it up to the speed we want it to be to serve the needs of this country. We're really living on our great-grandparents willing to spend money on roads, on bridges, on electric transmission lines. We haven't done that in a long time, and we have to get real about that.
Massive blackouts continue to be a global problem. 15 million people lost power in Europe in 2006, 60 million in Brazil and Paraguay in 2009, and more than 500 million in India in 2012. Such events have fueled the imagination of TV writers, who have added their own twist.
It's going to turn off and it will never, ever turn back on.
This may be fiction, but former Senator Dorgan, who worked for years on congressional energy committees and recently wrote a novel speculating about a terrorist attack on the power grid, says the threat today is bigger than a few down power lines.
We know from lots of anecdotal examples that the terrorists that use cyber terror are very inventive. They know that if they could bring down an electric power grid system, that would cause really maximum damage. This is a big, big challenge for our country.
The collective result of these kinds of attacks could be a cyber Pearl Harbor.
This week, more than 200 private and public energy companies will stage a large-scale mock blackout. No lights will go out, but the drill will test how government and utility workers would react if the grid went down.
If you bring down the electric power grid system in this country and it stays down for any length of time at all, it'll wreck the American economy. So we've got a lot at stake, and we better keep our eye on the ball.
So this was a video of the sequence of the events and some reports around it. Now, as mentioned, this leads naturally to the big picture structure of the North American power system. North America is organized into major interconnections. We have the eastern the Western interconnection plus separate Texas and the Quebec interconnection system as well. Alaska includes its isolated grids, but again, the main grids are color coded here, interconnected grids, as you can see. The interconnection structure matters because this disturbance can propagate within an interconnection if not contained. Also note the asset scale, trillions of dollars, over $1 trillion. So reliability is both a public and an economic imperative. The organization responsible for reliability standard is NERC. Let's define NERC. So NERC is a non-profit organization formed to ensure the reliability of North American bulk power system. Its main task is to develop and maintain reliability standards, and it coordinates with regional entities, emphasize the idea of bulk power system, transmission level infrastructure, and major generation resources. Now, let's name the main interconnection NERC covers. We have 4 interconnections. We have the 4 primary interconnections covered here are the Eastern, Western, Texas, and Quebec. Each has different operational characteristics and degrees of coupling, and reliability is implemented regionally through region entities. These regional entities, for example, WECC, MRO, NPCC, RFC, SERC, and Texas RE, support compliance, monitoring, and coordination. The structure has evolved over time. Previously, there were more entities. The key message here is reliability governance is layered, wide standard with regional enforcement and coordination. In the US, NERC is overseen by a federal regulator, the FERC. Now, FERC regulates interstate electricity transmission and wholesale markets, and it enforces reliability related regulations. In the US, FERC oversees NERC and the reliability framework. This is where engineering and policy meet. Standards, compliance, and enforcement impact how the grid is planned and operated. Now let's ground this in physical infrastructure where power plants are located. This map shows the geographic spread of US power plants. These show the power plants over 1 megawatts. The key points here is that generation is geographically diverse, therefore transmission and interconnection planning are essential for moving power to load centers. We'll use this to motivate why operations, market, and flexibility tools are needed. And you can see here Amarillo, the Panhandle area, and you can see we have a lot of wind energy and a coal power plant belonging to Xcel Energy and a few gas power plants around here. But you can see this is a wind corridor, and you can see a lot of winds around this area. Next, we'll look at what power system activities means across different time horizons. Now, power systems are managed across multiple time horizons. We have long-term planning in years, mid-term planning in months and weeks, short-term operations, days, hours, minutes, even seconds. Each horizon uses different models, data, and objectives, but they must be consistent. Let's zoom into operations and see how scheduling and dispatch work in practice. Modern operations must handle uncertainty, especially wind, renewable, and load variability. You can see the real-time regulation process in real time, and you can see the real-time market. These systems operate on structured timelines from day ahead to real time. This slide sets up the main idea. Operations happen in layers, getting more responsive as the real time approaches. Now I'll walk you through each layer and its typical time scale. We have day ahead unit commitment, which is 24 hours, which decides which units are on off to meet expected demand reliability and economically. We have intraday adjustment, which is between 1 and 4 hours. It will update commitments as forecasts and conditions change. We have real-time economic dispatch, 5 to 15 minutes. They will refine generation set points to balance supply-demand costs effectively. And then we have automatic generation control, or AGCs. It's 2 to 4 seconds. This is a fine control to maintain system frequency. So again, if system frequency drops or the voltage drops, it's going to turn on a emergency gas power plant or so on. Now, with these timescales in mind, we now discuss flexibility, starting with the transmission topology control. Traditionally, transmission is treated as a fixed network in short terms, but operators can and do reconfigure the topology. Then we have the topology control, transmission switching. This can reduce congestion, relieve violations, reduce losses, and lower costs. It's powerful but must be done safely. Switching changes flows and contingencies. Another fixed flexibility tool is power electronics based controls, what we call FACTS or FACTS. FACTS devices use power electronics to control AC transmission parameters like effective line reactances. They can increase transfer capability and reduce system generation costs by managing flow and voltage support. Think of FACTS as active knobs on the network rather than a passive lines. Flexibility also introduces new vulnerabilities, especially cyber vulnerabilities in monitoring and control. So, state estimation and false data injection, or FDI, cybersecurity becomes important here. State estimation is central. It converts raw measurement into an estimate of the system operating state. If measurements are compromised, a false data injection attack can mislead operators and downstream application. This is a high impact because operational tools trust the state estimator output. And FDI cyber attacks, as mentioned, can manipulate measurements. We have false measurements, may mislead system operators and cause physical consequences, and I'll give you some examples on that. Now let's map where state estimator sits in the real world operation loop. This is a graph which shows the current industry practices of power systems and real-time operations. We have the real-time RTU measurements. In real time, the loop is RTU measurements, and then state estimation, RTCA, which is the contingency analysis, and RTSCED, which is security constrained dispatch. This repeats continuously, so bad data can repeatedly drive bad decisions if not detected. The key technique point here is cyber defense, which includes data validation, bad data detection, redundancy, and secure architecture. Now we will pivot to score smart grid components, starting with renewables. So, as mentioned, core smart grid components, one of them is the renewable energy. RES, or renewable energy sources, are naturally replenished sources such as hydro, wind, solar, biomass, geothermal. Their key grid challenge is variability and intermittency, which creates uncertainty in scheduling and balancing. The wind doesn't always blow, the sun doesn't always shine, so you would have those uncertainties. This is why forecasting, flexibility, and storage becomes central in smart grids. Now we have AI and machine learning tools that gather a lot of data, like forecast weather and predict if we're going to have high wind or a cloudy day or a rainy day, and be able to adjust the system and use, for example, a power storage system like batteries to store the battery in advance to use them later. The most direct flexibility resource for variability to energy storage is energy storage, actually, as mentioned, like batteries or hydro storage. Energy storage systems, or EES, stores energy when it's available and releases it later. The key trade-off is energy density versus the power density. Sometimes the source of the energy could be renewable energy, like if you have a solar panel on your roof, you can store the energy during noon, or in the middle of the day when you don't use it, and then later on during the night when you don't have solar, you can use that. Sometimes the source of energy could be the grid itself, so you're going to store energy at midnight, from midnight to morning, when the demand is low, the electricity price are low, and then use that electricity during the day. The technologies for ESS include batteries, flywheels, pumped hydro, and compressed air. Some major applications are renewable integration, frequency support, load shifting, smoothing fluctuations, and black start capability. Now, to operate smarter at the distribution customer edge, we need better measurement and communication systems, or AMIs, what we call advanced metering infrastructure, or AMI, which includes smart meters, communication networks, and data management systems. The breakthrough is the two-way communication. Utilities now can measure in details and also implement programs on the demand side. AMI enables smart home integration and more granular pricing controls. One example that I can give, now in Houston it's being implemented in some parts, is the power company, the power provider, will actually give you a free smart thermostat like an Ecobee or a Google Nest, and if you connect them to the system and if they have control over it, they will give you subsidies and rebates on your electricity price. And the way that it works, during the high peak when the demand is high, the power company would, for example, in winter they will reduce the temperature inside the house by a couple of degrees, or in summer they would increase it. And imagine you have 100,000 homes connected, and the major consumer of power in the house is the HVAC system. And by replacing just that by 10-15%, they could avoid running very expensive emergency gas power plants, so save a lot of money and be able to manage. Instead of managing just the supply side, they can manage the demand side as well. With AMIs, we can actively shape demand. This is demand side management instead of the supply side management. Now, demand side manager, or DSM, includes direct load control programs, contract-based curtailment with compensations, the time of use pricing, or TOUs, which is currently being done in Amarillo. If you have a smart meter, you can pick a plan that your electricity is actually much cheaper during the midnight off-peak hours, and it's going to be much more expensive during the peak demand hours, which is 3 p.m. to 9 p.m. Again, that shifts in different seasons. And if you have, for example, an EV, it's going to be very beneficial that you charge your car overnight. Or you're running, I don't know, a dry cleaning business, it's better to run all your dryers during the night. Now, we also have real-time dynamic pricing, where whole house conditions influence retail pricing, and energy efficiency, delivering the same service with less consumption. DSM treats loads as controllable resources, not just a passive requirement. Next, we broaden the edge with view to include distributed generation and storage, DERs. DERs are decentralized, close to loads, and individually small but collectively significant. Some examples are distributed solar, wind, microturbines, behind-the-meter storage, and demand response. Some benefits include loss reduction, improved resilience, and reduced stress on bulk transmission. When DERs are coordinated as a system, we get a microgrid. Now, a microgrid, or MG, coordinates DERs and loads in a localized area, capable of operating in a controlled, autonomous way. High DER penetration and the inclusion of ESS help manage volatility and enable island operation during outages. Microgrids improve resilience and reduce burden on the bulk grid, and it has a lot of benefits. Finally, let's look at community microgrid concepts. This figure illustrates the community microgrid idea, combining local generation, storage, controllable loads, and a controller to support reliability. Highlight typical use cases are campuses, critical facilities, neighborhoods, and disaster resilience. Close with the course theme, we have the smart grids integrate operations plus markets plus sensing plus control and cybersecurity across the entire system. And next, we'll move from concepts into specific tools and models we'll use in this course. For the next class. Thank you so much. This is it for today's class. If you have any questions, just please email me. I would post the second set of quizzes immediately after I post this video, and you're going to have 1 week to respond to the quiz. Thank you so much, and have a great weekend.